So now that we have established a understanding of general transformations as well as matrix transformations, we are officially ready for linear transformations. Now I want you to note that the algebraic properties of matrix vector multiplication, so that matrix A times vector X, when we write this in function notation, this helps us to identify the most important class of transformations in linear algebra, the linear transformation. So here is our definition. And we say that we're going to let T from Rn to Rm be a matrix transformation. So we have the image of vector x under the action of T being defined as matrix A times vector x. And this is where A is some m by n matrix. Now we're also going to go ahead and let vector u and vector v be in the domain of our transformation. So in other words, vector u and vector v are in Rn. Our last condition is that we're going to let C be any scalar our little hearts desire. So then a transformation or a mapping or a function is said to be linear if the following two properties hold true. The first one is that the image of vector u plus vector v under the action of T is equivalent or equal to the image of vector u under the action of T plus the image of vector v under the action of T. And our second property is that the image of the scalar multiple C times vector u under the action of T is equal to the scalar multiple C multiplied by the image of vector u under the action of T. So these two properties make a transformation a linear transformation. So let's verify that these are holding true. Now, we want to keep in mind here that our transformation is being defined by the matrix transformation. So in other words, we can say that since the image of vector x under the action of T is computed using that matrix vector multiplication, we'll use this to verify properties 1 and properties 2. So let's start with property number 1. We have the image of vector u plus vector v under the action of T. Now again, since we know this is a matrix transformation, we can rewrite this as the product matrix A multiplied by the sum of the vectors u and vector v. So by properties of matrix vector multiplication, we can apply the distributive property and rewrite this as matrix A times vector u plus matrix A times vector v. Now, by definition of a matrix transformation, we can further rewrite this as the image of vector u under the action of T plus the image of vector v under the action of T. And oops, we did it! Woohoo! So our first property has been confirmed. Now, similarly, we want to go through and verify the second property, that the image of the scalar multiple of C times vector u under the action of T is equivalent to the scalar multiple of that image. So again, keeping in mind that our transformation is defined as a matrix transformation, we can rewrite this as matrix A multiplied by the scalar multiple C times vector u. Now, by properties of matrix vector multiplication, we can rewrite this as the scalar multiple C multiplied by the matrix vector multiplication, or matrix vector product, A times vector u. Now again, by definition of a matrix transformation, we can see that this is equivalent to saying we have the scalar multiple C multiplied by the image of vector u under the action of T. And again, oops, we did it! Woohoo! So we have verified that these two conditions of a linear transformation are in fact equivalent. And we can also make one final big conclusion here, just based off of this verification and definition, and that's that every matrix transformation is a linear transformation. So this is our final conclusion that we're observing by this definition. And again, that's every matrix transformation is a linear transformation. And we're able to make this conclusion simply by verifying the definition above. So every matrix transformation is a linear transformation. So this is the most important class of transformations in linear algebra, the linear transformation. And from this point forward, we'll be using our linear transformations quite frequently. Now, using this definition again, and these two verifications, we can attain the following properties about linear transformations. So let's take a look. So if we think back to the definition of a linear transformation that we just were introduced to and just verified, we observe that a linear transformation preserves the operations of vector addition, and we saw that by the image of vector u plus vector v under the action of t being equal to the sum of those two images under the action of t. And we also saw from this definition that linear transformations preserve the operation of scalar multiplication. And that was the second property, where we have the image of the scalar multiple c times vector u under the action of t being equal to the scalar multiple of that image. So linear transformations preserve these two operations, and this allows us to observe the following properties of linear transformations. So again, let's let vector u and vector v be in the domain of our transformation t, and we're also going to go ahead and let c and d be any scalars our little hearts desire. So then, if t is a linear transformation, then we can conclude that the image of the 0 vector under the action of t is equal to the 0 vector. And the second property that we can observe is that the image of the sum, or the linear combination of the scalar multiples c times vector u plus d times vector v under the action of t, this is equal to the sum of the scalar multiples of those images. So these are two additional properties of linear transformations, and they can again be easily verified using matrix vector multiplication and the definitions that we just observed. So let's take a peek. Now, as we go through this verification, let's keep in mind that we are assuming t is a linear transformation. So let's start by saying that since t is a linear transformation, then we automatically know that it preserves the operations of vector addition as well as scalar multiplication. So we know that the image of vector u plus vector v under the action of t is equal to the sum of those two images. So that's preserving the operation of vector addition. And we also know that since t is a linear transformation, that it preserves the operation of scalar multiplication, meaning that the image of the scalar multiple c times vector u under the action of t is equal to the scalar multiple of the image of vector u under the action of t. So we know right off the bat that these two properties hold true. So let's verify these two new properties. So property number 1, we have the image of the 0 vector under the action of t. Now, by properties of vector multiplication, we know that we can rewrite this as the image of a scalar multiple, specifically that scalar multiple is 0 multiplied by vector u. We know that that's equal to the 0 vector. Now, since linear transformations preserve scalar multiplication, we can rewrite this as the scalar multiple 0 multiplied by the vector, or the image of vector u, under the action of t. Now, we of course know that 0 multiplied by any vector is going to leave us with the 0 vector. And whoops, we did it. We have verified that first property. Woohoo! Now, let's go through the verification for our second property. So here we want to verify that the image of this linear combination of scalar multiples under the action of t is going to be equal to the sum of the scalar multiples. Well, again, since t is a linear transformation, we automatically know that it preserves the operation of vector addition. So we can rewrite this as the image of the scalar multiple c times vector u under the action of t plus the image of vector, or the image of the scalar multiple d times vector v under the action of t. Now, because linear transformations preserve the operation of scalar multiplication, we can further rewrite this as the scalar multiple c multiplied by the image of vector u under the action of t plus this scalar multiple d multiplied by the image of vector v under the action of t. Oops, we did it! Woohoo! So we have used the definition of a linear transformation to help verify these two new properties of linear transformations. And we can make one final generalization using the definition and these two new properties. So let's take a look. So here we go. We are going to take the definition and those two properties that we just looked at to come up with a generalized property for linear transformations. So here, we want to let vector v sub 1 through v sub p be vectors in the domain of our transformation t, and we're going to go ahead and let c sub 1 through c sub p be any scalars our little hearts desire. So, if t is a linear transformation, then we can make the following conclusion. And we can say that the image of the linear combination of all of these vectors, v sub 1 through v sub p, under the action of t, is going to be equal to the sum of all the scalar multiples of these images. So c sub 1 multiplied by the image of vector v sub 1 under the action of t, all the way up to the scalar multiple c sub p multiplied by the image of vector v sub p under the action of t. And again, we can use the definition of a linear transformation to help us verify that this is holding true. So, what do we know about linear transformations? So since t is a, and I'll abbreviate LT for linear transformation, since t is a linear transformation, we know that it preserves the operation of vector addition. So in other words, the image of vector u plus vector v under the action of t is equal to the sum of those two images. Now again, since t is a linear transformation, then by definition, we know that this preserves the operation of scalar multiplication. So in other words, the image of the scalar multiple c times vector u is equal to the scalar multiple of that image. And this, of course, is such that vector u and vector v are in the domain of our transformation, and that scalar c, well, is a scalar. So c is any scalar. So we automatically know that these two properties are being preserved because, again, t is a linear transformation. So let's use this definition to verify this generalized property. So we have the image of this linear combination of vector v sub 1 all the way through v sub p. Now, we know, since t is a linear transformation, that it preserves the operation of vector addition. So we can rewrite this as the sum of all the images. So we have the image of the scalar multiple c sub 1 times vector v sub 1 plus all the other images all the way up to the image of the scalar multiple C sub p times vector v sub p. Now again, since T is a linear transformation, we know that it preserves the operation of scalar multiplication. So we can rewrite this as the sum of all the scalar multiples of these images. So if the scalar multiple C sub 1 times the image of vector v sub 1 under the action of T, and we continue all the way up until we have the scalar multiple C sub p multiplied by the image of vector v sub p under the action of T. And that's exactly what we wanted! Woohoo! So we can see how we use the definition of a linear transformation to help us verify all of these properties. And we're going to be using all of these properties quite frequently throughout the remainder of the course.